Yeah, I'm Alexander. I'm the technical lead for what we call quantum-centric HPC at Pascal. So I just want to give some opinions and overview that we formed over the years at Pascal, integrating quantum and HPC. I'll just start giving some standard overview slide just to give some context perhaps of how our opinions have been formed. There's some very specific experiences that we've had that sort of I think shaped our view considerably. So I mean, from Pascal, we're a quantum hardware vendor. We have neutral atoms based QPUs. So that means we manipulate the state of atoms using lasers. I'm not going to go into great detail on this today, but effectively, over the past 5-6 years, this technology has really matured significantly. So there's also a bit of a staging difference maybe in the photos, but we really, I think, made great progress. And having interacted with the HPC community, some years, I'm wondering, have we, on the point of view of hardware, I think we really sort of changed our viewpoints from what we had just a few years ago when we were thinking that, putting this hardware inside the data center was going to be a potentially difficult task, whereas now, quite a few vendors have been able to do this without too much issue. In our case, we have, for example, put up two QPUs at the CEA in France and Jülich in Germany that have been inaugurated last year. Yeah, and we've also have them available in the cloud and further installations coming up. But on to more interesting topics. So we're a full stack company. We also write software. Pascal's technology, the one we have currently deployed, is analog. We have a fault tolerant program as well. We've made our first logical qubits, but for now our commercially sold machines remain analog. So that also means that we really do have to write all of the software stack on our own. So we have the application layer library. We have some more user-friendly SDKs that's currently in development called Coolkit. We have Pulsar that maybe some of you have experimented with in the past. We've had integration now with external SDKs like NVIDIA's CUDA-Q, IBM's Qiskit, and Evidence MyQLM Captiva platform, which is actually the one that is being used on the machines we have available at Jülich and the CEA. This was the integration form there. And there's actually something that I think has also shaped our view on many topics in the HPC integration space, because on one side, this is great because Evidence is also the system integrator for those main clusters. So everything there was done, natively by the system integrator and supported by them. But it also means that the core of this software stack that integrates our machines is proprietary and not our own. We don't have access to it. We can't. We don't really have any visibility to what happens in the middle, right? So for us, we can have access to the user, to help to write libraries that the user can use to program our device, and we have the device itself, but there's a black box for us in the in the middle. This has been, I think, quite formative of some of our opinions. Now we quite like open source in this layer, and we're also a bit we don't want to have to go into too much, put too much complexity that is not transparent, and that's something to keep in mind when I present something I'll present later, because you might think it's inconsistency. But so yeah, this should maybe gone before, but HPC integration these days looks mostly to be a software issue, but I view it also mostly right now through the user enablement glasses. We don't think too much about maybe performance optimization, latency reduction, really instead just trying to enable users, enable even like the tool builders and admins to be able to perform the integration work. I think this is right now a far more important topic than trying to figure out, think too much about latency, or these discussions. We often end up talking about tight integration versus loose integration and various of these integration models. I don't like it too much. I mean, I feel we should be able to have some software, at least from the vendor perspective, software that works in all environments as much as possible. So yeah, for this, we also, I like to think about the full development workflow, especially these days. I think, traditional HPC, we have, applications that have been maintained over decades, and they're very well written, they're optimized, maybe a bit legacy code, but it's really mostly about executing applications. Whereas now in quantum, we still have to develop all of that, and sort of the development workflow, I think, becomes a very important part of it. So whenever we discuss these sort of integration topics, I want to always try to think about how will the developer experience dealing with this, and also how can we make this interoperable with cloud available QPUs. We see, especially at least internally, people tend to want to switch between the different QPUs, different access models. And even though this might be out of scope for the HPC Center, I don't think it's going to be, I think the users that access the QPUs from the HPC will still feel largely the same way. So one of our most important work streams recently, I'm not going to go into much details about, because it's about resource management and the quantum resource management interface that was presented here in this topic by our colleagues at IBM about a month ago. So instead, you can go and find that. I think this recording's available even. So you should go and look at that. But just to refresh memory, since I will be building on this, the QRMI is the simple, thin, vendor-agnostic middleware layer that helps, provide the connection between the user code and the QPU, integrated with Slurm, so it becomes a schedulable resource, and you can do, --QPU in Slurm. We also tried, I know IBM has worked with some of the schedulers, and now at Pasqal we've also spoken to some other resource managers to consider moving it beyond just Slurm. Yeah, I'm not gonna say too much on this. How it works, pretty simple configuration with a config file. you can use Slurm commands to send the job, and then you just one thing you have to make sure of is to use the correct Python library to submit the code. I just remembered back at supercomputing, there was in one of the quantum HPC workshops, someone mentioned that, you know, every time a quantum vendor talks about their Python library, HPC person dies inside. And I thought that was a good point. But there's also, as I brought up at the time, every time I talk about a C API, my quantum algorithms team also die inside. So there's going to be, I think we still have, you know, a long time before we can bring the people that, you know, develop quantum algorithms onto the C heavy environments. Yes. So onto our sort of the on-prem QPU setup. Maybe I should say beforehand, as far as the QRMI is concerned, we can work with both on-prem and cloud-based QPUs, but I think this forum is most interesting to deal with the on-prem details. So we're mostly looking at the access model based on a quantum access node. So there will be a dedicated node that will have the connection between the QPU and the node. This is maybe mostly a networking issue, but I think I've thought about this quite a bit, and I think it sort of makes the most sense, and it simplifies things, and I hope that, you know, the QPUs available in HPC centers have enough usage that one does not regret having a single node taken for this. But the thing we're developing at the moment is we're going to start a middleware daemon that will run on the quantum access node. It's labeled here administration area, so it's intended to be outside of the access of the normal user. So we'll just expose a REST API that they can speak with. In fact, the QRMI will actually speak with this daemon, not the QPU itself. So this will be one or two daemons. We played quite a bit with both ideas. So it might be a user area and an admin area, or they might go in the same daemon, but that's a implementation detail. So it will enable both the user interaction, submitting jobs, getting device information, and also act as you know, sort of single access point also for administration reasons, so that you can have this to be aware of the device status, the logs. From the vendor perspective, we can feel a bit easier about who accesses the API on the QPU perhaps as well. So you can start putting more things into these daemons. And the idea is actually as well to open source it, or at least share code with the users, or sorry, with the center, the customers, as we've found that they all have so bespoke setups that is very difficult to provide a good experience using a standardized API, and also that they want to have some ability to configure things, especially at the scheduler level. So this middleware will actually have a second level scheduler. And the idea there is that so this, to be very honest, you know, this idea also originated from a request in a tender where we had to allow multiple users to access the QPU at the same time and there was some level of configuration that was required. And so we thought that, this is not a bad idea, because we can have this simple scheduler there. We can add some configuration options there for the sysadmins, so they can set in policies, priorities. We can expose some level of admin controls on this queue, and we can do this much more easily than we could do if we put this piece of code on the QPU itself, at least the way our internal stack is structured. And we get sometimes we can let the system-wide scheduler, be it Slurm or something else, handle all the things that they do well. So fair share, node allocation. We want to think about this part as little as possible. So we thought, for example, this was also very, very interesting to think about in terms of defining job classes. So you might find that you have, let's call them production jobs. So real, users executing real workloads where they want to have exclusive access to the QPU, or they want to be sure that they can preempt anything ahead of them because they have a long running simulation. But if the QPU is free, you can enable submitting short development jobs, test jobs, monitoring jobs. So we found that some centers, they like to schedule periodically their own jobs for various reasons, but to monitor the state of the system. So this will enable them to do this directly in the QPU queue, let's say. And we can make this queue calibration aware. This is going to be a bit more difficult, I think, on our side, because you have in the QPU itself, in its operating system, it will take care of many, say, minor calibrations almost continuously. But this, of course, would be an interesting thing to take out. So we have, one of our customers, Chinica, having a QPU being set up right now, and they do a lot of research in malleable jobs, so like the dynamic resource allocations, and they had a lot of, and partners had many quite interesting ideas. For they published a paper almost a year ago. So yeah, this was part of the motivation there. We don't have much, let's say, concrete to show yet, but we've done a lot of preliminary work, started developing and thought about this. I'd love some feedback on this. Yeah, going back to what I said before, that I with the machines we have connected via Captiva, this was then sort of trying to provide be able to sort of fix all the issues that we can see with that experience, and that's really why we think this is going to be a very cool idea, even though second level scheduler, second queue, it's not intuitively a nice idea, but it seems to be good. This is part of our work stream on trying to provide a, let's say, more user-centric environment. So in particular, especially in our case, I would say that we're seeing more and more variety in the execution environment of the user. So basically, a lot of bugs can accumulate as the user tries to develop code on their laptop, versus develop code on the HPC system versus develop code in cloud. I've heard from the HPC community that okay, but then you would do, let's say, the normal thing in HPC, which is develop on the HPC node, which would indeed also be a mitigating thing here, but it's just not my experience dealing with real users. So in particular, just this idea of having, enabling more frequent testing using local emulation. The fact that we can't debug quantum programs very well means that, for me, it has much more success rate to debug the workflow or like the overall hybrid program. I think this is really a key concern at the moment. And then you can move this over to the system, and you can sort of repeat those tests, but even closer to the execution environment of the final run. Yeah, we have some internal experiences which shown good improvement in let's say silly errors, I would call them, but they can be quite devastating. Almost at the end, actually. Going fast today. So yeah, loose end was one that I was mentioning before, was the runtime environment consistency. But the other thing was, I didn't find a good way of expressing in slides, but it was sort of observability, monitoring, access to data from the QPU. So when you run a quantum program, you might want to have access to, you need access to the calibration, or if you run two different executions same program over time and you see very different results, you might need to find out what's the, what changed. This is somewhat of a black box. You don't have too much ability to debug it, right? And the user will need access to this, right? And as a vendor, this is touchy subject, exactly what you can expose and where you can expose it. But I think it would be extremely important that we find a good solution to this. I don't think this is something that we can standardize, because systems will be very different. But I think there's a great importance of having a holistic software environment when we approach this. In summary, having gone much faster than intended, yeah, we're currently working mostly on the idea of scheduling, resource or job management, trying to figure out how to schedule quantum jobs, trying to do this in a way which enables everyone to configure the overall system as much as possible, and perhaps do their own research or do their own performance improvements, and also trying to tackle this idea of a sort of holistic environment, almost a portable environment, we can say as well, where the user can access, can run the same program as much as possible in different places, and especially in the concept of a Python program, right? I think there are issues that we're seeing that would be lessened by a fully compiled program as well. That is a criticism that I got, and it's very valid. But again, I don't see quantum algorithm developers changing their habits of Python so fast, and I really think that also from the point of view of the HPC community, it would be great if we can try to solve it in such a way. That was it, actually. Thank you very much. I hope there's some questions.
Thanks, Alexander. Yeah, the floor is open for questions. I have a whole bunch, but I'll let people go first. I think Jorge and then Kevin. Go ahead.
Hi, Alexander.
Hey.
Actually, hi everyone. So when you were mentioning the second level scheduling approach, it's actually, I find it quite interesting because it's the same approach we are following in openQSE. I'm mentioning this because now that we are talking about trying to keep QRMI and QRMI sort of compatible, maybe we should also start talking about this one, the second level scheduling approach, because there might be something we can also do together.
Yes, definitely. And I think even just in the form we're in right now, I saw there's even a bit of a spec on the GitHub repo by Amir, I think, for second level scheduler, which is actually how I came up with the idea on the slide of having second level scheduler as the name. So I think this would be great to everyone who's done work in this area to come together and speak. I think especially from the center perspective, you will have multiple devices for multiple vendors to consider as well, which is a issue that I don't have to deal with. So it'll be very interesting to hear.
Thanks for the talk, Alex.
Thanks, Jorge.
Kevin?
Hi, Alex. Thanks a lot. A question about the integrate. There was one thing you were mentioning, that there was the black box that was in the flow that wasn't open source. I believe you were referring to the Captiva package, but I haven't worked with Captiva. Is that what you're referring to, something that was entirely proprietary? Yeah. Again, this particular group's focus is on basically trying to realize an open source stack, all the way from the user to the devices as close as we can get, and for HPC. From your standpoint, do you see any promising open source? What open source alternative do you think might be close enough to Captiva for you to be able to substitute that if you wanted to have a fully open source integration?
So, I mean, on our front right now, the Captiva is, so we are the vendor of the QPU, right? So the Captiva is on the site of the HPC Center, and I cannot control what they want to do. I mean, this was the original HPC-QS tender that was written 5 years ago or whatever, when there were a few vendors who were willing to take on the risk of doing this. So Eviden was willing to do this, right? I don't think there's anything. I mean, we're a part of the QRMI initiative. Unique community. They have their own QDMI specification, right? So I think both of these initiatives are targeting this kind of problem, and I'm not sure yet. So I think what's interesting, right? What's very nice from the Captiva point of view, if you're a procurer, is that they are also the system integrator. So they are all really responsible there for the whole system. So that would be, I think, the biggest hurdle right now to overcome and to get sufficient traction behind either the QRMI or the QDMI or both, because we end up making them completely compatible. Yeah. I fear I said many words and didn't answer anything concrete, but
thank you.
Thank you.
I had a few questions. I'll pick one of them now. So from the top, when you schedule, first, do you schedule both the classical and the quantum at the same time? Or do you always have this idea of an access node that is tied with your QPU so that when you allocate the quantum portion of your job, you're always getting the access node with the quantum portion?
So, I mean, so right now we're considering having the quantum access node fixed, but that is a worker node, right? So you first ask Slurm to schedule a node for you. I mean, to schedule the queue for you. That means that
Did you lose Alexander?
Okay, I was concerned it was my end. Okay.
No, I think he said they cut his fiber and he's on a wireless. So you'll join in a second. It's actually, oh, he's back. Good.
Hey, thanks. Sorry, as I mentioned, I'm on the phone internet. Where was I? What was the last thing you had?
The worker node, you're saying the quantum access node, when you reserve, you ask the HPC for a worker node?
Yeah. So, you know, for me, it's mostly a networking issue. Like, do you really keep the quantum access node sort of permanently there or not? So, yes, in my day-to-day, I basically assume that it's fixed, but I'm also, you know, I don't think that's necessarily the case. Especially if you don't care about sort of the latency, which I don't think you should at this level, you can definitely route that traffic however you want and have it accessible from any device. The only issue that we're seeing right now is that a lot of the logic that's currently in schedulers like Slurm, you know, it comes from GPUs. So there's a certain assumption there on that the thing you're tagging is fixed to a node. So I think that's going to be the main like short-term hurdle, but from the quantum point of view, it's not really. You can also solve this by adding like an intermediate node or adding more classical resources on the quantum side. But I also don't think that's maybe the most popular opinion from the HPC community. For me, I'm completely agnostic to it. I don't see a difference.
I have another question, but if anybody else wants to jump online.
Maybe a follow-up on Amir's question, right? So let's answer Yogesh here. So just to understand, so does it mean that scheduling this particular quantum, allocating this particular quantum access node to the user automatically allocates the QPU to that user exclusively?
Oh, I think it's frozen again.
Or he's very still and not moving.
Yeah, I think.
There's a fiber issue, I'm guessing. Yeah. But did you quite catch that, Amir, earlier on when you were mentioning?
I think what he was saying is that he went off. The quantum access node is allocated like the user explicitly requests it, and then here he is. I'll let him answer. Yeah.
I was not sure if you caught the question, Alexander. So
I heard the beginning, but not the full. I'm going to turn the camera to see if it helps.
Is the quantum access node sort of tightly coupled to the QPU so that allocating that particular sort of node to the user automatically gives exclusive access to the QPU to that user for the duration of the allocation?
It's coupled only in software. Well,
Gotcha.
and there's a networking port. I mean, there's going to be currently a Ethernet cable, right? But a networking cable between the node and the QPU. But otherwise, there's software. Yeah, I should say, okay, that's another point there, maybe, that for some cases, it's nice to be able to install software on a specific node. So either you take a fixed node of HPC and couple it to it, or you might need to have a tertiary node in there to be able to install software on it. But for me, that's just a discussion between the center and the vendor, exactly how they want it done. But it seems that, yeah, at least there was a move at some point, I feel, that to people not wanting to have another node installed. They wanted to really have it on the main cluster.
Thanks.
All right, I have a question. So when you submit the job, right, like to the quantum, or I guess to the access node, what are you submitting? Are you submitting a circuit that gets executed on the QPU, or are you submitting a Python script that runs on the access node?
Right. So it's a normal worker node. So it runs the full the Python script that you submit, right? It's just it's designed to run a hybrid program. So it will run the Slurm, the bash script that Slurm gets. That would be the idea.
Okay. So in that sense, then a hybrid program, like if we step up a level, you have like a big simulation sort of environment where you're executing some large simulation. Portions of it are just pure classical, and portions of it are offloaded to the quantum. Now, how, like, is it that you allocate both HPC and the quantum resources at the same time, or do you just right now only support the workflow where you do some classical, generate your, Python stuff that you need to execute, then you release the classical, and then you start executing the quantum? Is that the flow that you currently support, or do you support also the cost or the co-allocation of both HPC and quantum at the same time?
Thanks. Right now we're looking at the co-scheduled job, but it really is fully dedicated for me to the scheduler. So I mean, if the user wants a co-scheduled job, then they get a co-scheduled job. If the user wants to write a more complex Slurm script, then they can also avoid it, right? They can not co-schedule them. Runtime will be longer, but probably budget would be less.
Lee, go ahead.
Yeah, thanks very much for the talk, Alexander. Quick question, I guess, on my side from, I guess, maybe jumping off from Amir's question on what you're sending in to execute. Do you have like some structure that you can represent as part of the program? So I mean, assuming you have a hybrid job where classical and quantum instructions are represented, I mean, do you expect a compiled payload to go in with branching instructions, with for loops, with kind of nested regions? I mean, how are you handling that with this type of environments?
So for right now, the code that would run on the quantum access node would be the full classical code, right? It's a normal code. You would just communicate to the QPU with the REST API at the moment, like with the HTTP client. Then on the QPU side, we currently just have the serialized program. Exactly how we will deal with this in the future, as I'm sure you know, once we talk about large fault tolerant program, this payload is going to be pretty big. That's a question that I decided to leave for the future, because I think it will change. But that also depends on exactly what kind of coupling mechanism exists between the QPU and the main code, right?
Yeah, absolutely. I mean, that's exactly where I was going to go on the QEC stuff. But yeah, happy to come back to that later.
Yeah, I mean, basically, we consider the QPU to be the highest level resource we could imagine from the QPU side. So there's no, right now I don't want to think about having like the KEC hardware running on the HPC itself, right? Because there's you want to know what runs on the hardware that needs to respond to your KEC algorithm, right? So it's really the highest possible level quantum program that currently goes.
Gotcha. So the program itself you're sending in would be treated effectively as everything here is running on logical, let's say, qubits in the long run.
Yeah.
And you're going to hide the details of the physical. Gotcha. Perfect.
Yeah, exactly.
I can go if nobody else has questions. All right, so drawing on that like the discussion we just had, when you said you deployed a couple of machines in different data centers, is the access to those machines exactly like the cloud access, right? Like you still use REST API to submit all those requests to the machine, or is there like a lower level API that is targeted for on-prem deployment rather than cloud? I guess the difference is an interesting question that came up before is what is the advantage of on-prem if we're just deploying it exactly like cloud?
Exactly. Currently, it's the same. It's a different client, but it is the same type of client. It's a REST API. As to the benefit, I mean, you can ask the same thing about HPC in general, right? Why do you bother procuring a system on site instead of just renting it in the cloud? I think it's much the same, but I think we need to do the work and figure out, we don't know what a useful quantum program will look like in the future fully yet, right? So we have to figure it out first before we can, assume which model would be more beneficial. But especially for neutral atoms, I think with ion traps, we're not in a low latency regime. So that's really not high on our priority list.
Hakim, go ahead.
Thank you, thank you, Alexander, for the talk. I wanted to ask you if currently you're operating on assuming that the jobs are a mix of hybrid and a hybrid of quantum and classical code. Do you plan to work with something similar to how Q# works, where Q# is a specific programming language for quantum only, and how you support jobs that use Q# or similar programming languages that might appear in the future?
I have to admit, not familiar with Q# beyond knowing it exists. So I mean, our currently commercial QPUs, they're in the analog regime, so we don't deal with digital gates. So that's we have fault tolerant machines in house. Yeah, exactly how to respond to this question, not quite sure. I spent some time in the programming language community, and I decided that anything can be a programming language if you decide so when you when you write it, right? So I like the model of hybrid languages that can do both the quantum and classical in a single source program. But again, if we're dealing with Python, then don't care too much.
Yeah. Sure, thank you.
Lee, go ahead.
Yeah, maybe just to come back to something I think you mentioned that earlier, Alexander, about your HPC people want your C APIs, and then your algorithm developers want to live in Python land. Have you given any thought to like using an embedded, like a shallowly embedded DSL? I mean, I think like this is the way we do it with Penny Lane with the catalog provider. That the language has a specific set of constructs that compile into an intermediary representation, which is then fully targetable by LLVM and then down to C layer application. So you kind of get the best of both worlds without scaring people away from the algorithms layer who want to just NumPy in Python code. I mean, I guess, do you have any thoughts on something like that as a kind of a bridging way to get into, converting people from both sides to, hey, we can meet in the middle and do it something like this way?
I personally really like Penny Lane, so yeah, we were looking down the route of doing something similar ourselves for a while. We eventually decided to not go further on that path. Yeah, I think it's a very, very likely scenario. I think, yeah, we'll have to see. I don't want to get too much into the details of comparing different libraries. But it's definitely, I mean, the DSL approach is very, very interesting, and it was very successful, right, with the PyTorch, for example, in the machine learning world. So,
Yogesh, go ahead.
thanks.
Yeah. So one of the application classes we're targeting are the SQD applications, where the use of the quantum comes in right at the beginning, right? And beyond that, it's mostly just HPC. In such cases, when you're scheduling it, right? So together, so would you sort of want to first schedule the quantum separately and get the results from that, and then sort of independently start scheduling the large HPC compute? Because that will be a little kludgy on the user side, right? Because by the time sort of you get the results from the quantum, you might get into a very long queue for the rest of the HPC, right? On the other hand, if you sort of try to schedule acquire both together, you will be keeping the quantum idle, right? While you're running the big HPC post quantum sort of initialization, right? Any thoughts on that?
Yeah, I mean, that's basically part of the reason why we did this second layer scheduler, because then people can have access to the kind of access to the QPU without being the one that uses it at the moment. I think, yeah, that SQD approach is quite interesting. I think it's definitely, I see some people criticize it as being a bit too NISQ specific, but at the same time, I think once we start to look into really combining quantum and HPC jobs, I still think we might see more of it. And that's also why we try to leave as much flexibility in the scheduling step as possible to enable both sort of logically tightly coupled co-scheduled jobs, but also these much looser ones. I don't want to prescribe the usage model too much on people, and hopefully someone will do the research and figure out how to use it.
Thanks.
Thanks.
I wanted to bounce on the second level scheduler concept again. So you mentioned that the second level schedule is there to allow multiple jobs. I guess when you say jobs, you're talking about Slurm jobs, right?
Yeah.
So you have multiple Slurm jobs. Each one of them has different quantum workloads they need to execute. And you need to be able to have your machine or the quantum computer handle those different tasks that are coming from the different jobs. Now, how do you determine, or did you have you guys figured out a good way to sort of limit the number of tasks that are queued on the quantum computer such that like those jobs that are waiting for results are not waiting forever?
Yeah, I mean, there's two approaches that I'm aware of that you can do. One thing is you can use a license, right, and limit access to the resource with the license in Slurm. The other one would be to develop the GRESS in being Slurm specific, but like something like a GRESS resource. So that's something we're currently looking at to enable that. I'm sorry, I forgot if there was anything more to the question.
No, it's I'm just wondering because you can assign a specific number of licenses, but are those licenses per quantum task that a job generates, or is it per job? Like when a job comes in and it wants to use the quantum, it obtains a license, and then now it's able to just submit a whole bunch of quantum jobs or quantum tasks. I don't want to overload
Right. Yeah. So I mean, you use that mechanism to limit the amount of concurrent accesses that there can be, and then in the second level schedule, there's a priority queue, so you can assign a priority. That priority, we're still looking exactly how to define before we put it into production, but it's going to be a mixture of the actual job priority in Slurm. There might be multiple queues that have access to this device, right? So one thing that we talked about was maybe you have real production jobs, but also development and testing queues. So maybe you want to access, for example, have some low priority test job be able to be preempted, right? So if someone comes in and says, "Hey, I'm running a real program here. Please let me," and then the scheduler will just cancel the job on the QPU. That can be done very quickly, and then preempt it. Again, on our machine, we're not in a low latency regime, so that overhead is very, very acceptable to do that. And then yeah, this is supposed to be configurable. Maybe you can come with a better way of doing it down the road. You can also, for example, if you have 10 licenses or 10 GRESS exposed to the node, you can imagine that if someone asks for one GRESS, then that's 1/10 of the QPU resource over time. Whereas if they ask for 10, then they have exclusive access, and we can deal with this using normal budgeting mechanisms, right?
Yeah.
The counting here for us, the point is that the accounting should not be done by us in this middleware. The accounting should be held in the Slurm database or wherever the center decides to host the accounting.
Makes sense. Thank you. Yogesh, go ahead.
Thanks.
Yeah, so I know we're hitting the top of the hour, so I'll keep it quick. So this might be a bit of a niche question because one of the nice things, Alexander, that you talked about is the ability to move to the cloud as a quantum hardware in addition to HPC. And so most of the work that we've done in the last couple of years is more on the quantum plus cloud, right? And HPC is a newer area more recently. And one thing that we see is long queuing times and non-deterministic queuing times on the quantum running on the cloud. Right, so if you have your jump node that's going to be pushing to a cloud sort of queue rather than the local captive quantum resource, right? So how do you see that working? Do you see this only for reserved quantum instances or for things that go into a longer queue as well?
Yeah, I think this is a enterprise level feature, so you should, would expect that you would have to have enterprise features on the cloud side as well. Yeah, I forgot to mention this before, but both for cloud, but also for on-prem, one key issue that is easy to forget is that you have to respect the wall time allocated to the main job, right? So if you have a a job running on HPC, you have a max hold time, and then that's something you have to respect, and that's a bit of a key constraint as well. So we have to figure out how to, yeah, as you said, like make that predictable, right? Because currently it's not.
Absolutely, and we actually hit that frequently because we use fast workflows for launching some of these quantum jobs, and we hit the 15-minute limit of these fast functions, right? So we had to come up with a very complicated asynchronous polling mechanism. It goes off to sleep, gives up its slot, comes back up again using a timer after a few minutes or so. And some of even the estimates given by the cloud queue seems to be fairly non-deterministic, right? So you might come back after 10 minutes hoping it's ready, but it's not ready, and you go back to sleep and so on. So it can be a bit tricky if you don't have exclusive nodes on the cloud. Yeah.
Exactly. We actually had something funny internally recently where someone spent a few hundred, maybe $1,000 just pulling for something that, because the machine was done for maintenance, but they were pulling our API, pulling out data constantly for like 4 weeks. I think that's another, yeah, there are many of these things that you don't hit before you try. So a great example.
Sounds good. I think we're at the top of the hour now. Thank you, everyone. And thank you for our US folks who came on the holiday. Sorry about that. All right. Take care, guys. See you. Thank you,
Bye,
Alexander, for the talk. Alexander, if you can send me the slides, that's okay. I'll include them in the.
Yeah, I will get them to you tomorrow once I have proper internet. Thanks, Amir.
Thank you.
And thanks, everyone.
Take care, guys.
Bye bye, everyone.
Thank you. Bye bye.
Thank you.